Here's a dice problem from one of the interviews for a quant role. The question says, on average, how many times must a fair six-sided die be rolled until there are two rolls in a row that differ by 1, such as 2 followed by a 1, or a 3, or a 6 followed by a 5. So in the previous few videos, we have solved similar problems. We've used Markov process, Markov chains, expected value calculation. In this question also, we'll use these concepts, plus we'll use the concept of symmetry to reduce the number of unknown variables. So let's see how we solve this. So let E be the number of rolls required until the stopping condition is reached. Suppose we have just rolled a number I on the die. Then the number of rolls required going forward is given by EI. Additional rolls required from this position. Now, the most important part of this question is realizing the symmetry which we have here. That is, the number of rolls required when you've just rolled a 1 is the same as the number of rolls required when you just roll a 6. Similarly, the number of rolls required when you just rolled a 2 is the same as the number of rolls required when you just roll a 5, and similarly for 3 and 4. Now, you can think about it this way. If you have the numbers here 1, 2, 3, 4, 5, and 6. Let's say you just rolled a 1. Now, in this case, your success condition is given by 2. So if you roll 2 on the next turn, you have reached your final state, which is the absorbing state. Similarly, when you just roll a 6, your next roll, if it's a 5, you would again reach the absorbing state. And this happens with probability 1 by 6. In this case also it's 1 by 6. Number 3 and 4 probability is again 1 by 6, and you just reach the state 3 and 4. It does not contribute to the success criteria. Similarly, if you just rolled a 2 here and the next roll is 3, you would be reaching the success state. Or if you roll a 1, in that case also you would be reaching the success state. The same thing happens when you've just rolled a 5. Your success happens if you just roll a 4 or a 6. Both of them happen with the same probability, which is 1 by 6. Same thing happens in the case of 3 and 4. So the number of rolls required from each of these states is the same. So E1 equals E6, E2 equals E5, E3 equals E4. Now, we'll look at a more formal proof for this in a different video. But for now, this symmetry holds true. So how can we write the total overall expectation? So the total number of rolls required is E. As we have seen in a lot of different previous videos, how do we write this recursive equations for the expected rolls is the total number of rolls required was 1 roll plus, when you roll a die once, you either roll a 1, a 2, or any number till 6. So each of them with probability 1 by 6. So let's say you roll a 1, that happens with probability 1 by 6. So this gives you 1 by 6 times you reach the state 1, and from 1 the number of rolls required to reach the final state is E1. So the total roll becomes 1 by 6 times E1, plus you roll a 2 with probability 1 by 6 and you reach state 2. The number of rolls required from state 2 is E2, so you get 1 by 6 times E2, and so on till E6. So this gives us this equation. Now from symmetry, we have seen E1 equals E6, E2 equals E5, E3 equals E4. So we replace these variables in the equation to get this E equals 1 plus 2 by 6 times E1, E2, E3. Now we have 4 variables, and we need to write more equations. So let's say we just roll a 1. We just rolled a 1. So this should say state 1 actually. Yeah. The expected rolls required from here is E1. Now from 1, the next roll can be either 1 with probability 1 by 6, and we stay in state A. We roll a 2 with probability 1 by 6, and this gives us a success because the difference between this roll and the previous roll is 1. So we roll 3, probability 1 by 6, move to state 3, and E3 is the number of rolls required from here onwards. We roll a 4, probability 1 by 6, move to state 4, number of rolls required from here, E4. Roll a 5, probability 1 by 6, move to state 5, number of rolls required from here, E5. We roll a 6, probability 1 by 6, move to state 6, number of rolls required from here onwards is E6. Now, So we have this probability states. This gives, we can write the equation for E1, which is number of rolls required from this state 1 to reach the success criteria, or the absorbing state, is 1 plus 1 by 6 times E1, which is from here, plus 1 by 6 times this second one, which is our success state, E2, which would be 0 because this is our success state. We have reached the absorbing state. So this gives us 1 by 6 times E1 plus 1 by 6 times 0, this part. Similarly, 1 by 6 times E3 plus 1 by 6 times E4, 1 by 6 times E5, and 1 by 6 times E6. Now, once again, we will apply the symmetry. So E1 equals E6, E2 equals E5, E4 equals E3. Substituting this into our above equation, we get this equation, and then we collect the like terms on one side. This gives us an equation in E1, E2, and E3. Similarly, let's say we just roll a 2, which means we are in state 2. The expected rolls required from here is E2. Now we roll a 1 with probability 1 by 6, and it gives us success because the difference is 1. We roll a 2, probability 1 by 6, and we go to state 2. Number of rolls required here is E2. Similarly, for E3, we get success again because the difference is again 1. 4, we go to state 4, and similarly for 5 and 6. Once again, we write the equation just like we wrote it previously. E2 equals, the number of rolls required from state 2 is 1 plus 1 by 6 times this one, the first one, which is the success criteria. So we don't require any rolls from this position because this is already the absorbing state, plus 1 by 6 times E2 plus 1 by 6 times E3 is again 0 because this is also a success state, 1 by 6 times E4 and E5 and E6. This gives us this equation over here. Once again, we use symmetry and collect the terms on one side to get another equation in E1, E2, E3. So far, we have 3 variables, E1, E2, E3, and 2 equations. We need one more equation so that we have 3 equations and 3 unknowns, E1, E2, E3, and we'll be able to solve them. So we follow the same process for 3. From the we just roll a 3, so we are in state 3. The next roll can be 1, 2, 3, 4, 5, 6. Same process. From 1, if we roll a 1 with probably 1 by 6, move to state 1. From 2, we get a success because the difference is 1. From 3, probably 1 by 6, we stay in state 3. We roll a 4, probably 1 by 6, again a success. Roll a 5, probably 1 by 6, move to state 5. We roll a 6 and move to state 6. So these two are success ones. This one, so these become 0. So the equation becomes E3 equals 1 plus 1 by 6 times E1 plus 1 by 6 times 0 because it's a success. 1 by 6 times E3, this one, plus 1 by 6 times 0. This is the fourth one, this one, plus 1 by 6 times E5 and 1 by 6 times E6. Once again, we use the success criteria. The symmetry conditions. E5 equals E2, E1 equals E6. We get another equation in E1, E2, and E3. So now we have 3 equations and 3 unknowns. So we can solve this equation to get the variables. So solving these equations, we get E1 equals 70 by 17, E2 equals 58 by 17, and E3 equals 60 by 17. Now, time for the final answer. So recall that initially we had E, which was the total number of rolls required, which was 1 plus 2 by 6 times E1 plus E2, E3. We substitute these values and we get the final answer equals 239 by 51, which is 4.686. So how do we interpret this? On average, you must roll a fair die approximately 4.68 times before 2 consecutive rolls differ by exactly 1. So that was the first part of the problem. We have another part here, which you can probably read on dataloopr.com/blog. The question says, what if we stop when 2 consecutive differ by no more than 1? Thanks for watching, and I'll see you in the next video.